This video will lead you through the solutions for problems 3 and 4 on the rotational motion problems packet. So go ahead and read problem 3 to yourself and start solving it on your own. Pause the video when you're solving it, but if you get stuck or if you want to see the solution, unpause the video and I'll give some hints and then eventually I'll give the whole solution. So you might notice that you're given the time for the initial motion of the salad spinner, but then you're not given the time for the motion as it comes to rest. So this may lead you to think that maybe you want to use your time-independent kinematics equation, since there's no point in finding the time it takes for it to come to rest. However, to use your time-independent kinematics equation, you have to know the initial angular speed of the salad spinner, and that's why you can use the 5 seconds. So the first thing you want to do is find the initial speed by using delta theta over t. It goes through 20 revolutions. That's what it's saying when it turns 20 times. So 20 revolutions, which you have to turn into radians by using our conversion factor of 2 pi radians per revolution. Divide that by the 5 seconds, you get 25.1 radians per second. And now you're set to use the time-independent kinematics equation. So here's the equation to solve for alpha, which is the angular acceleration. So it's omega final squared minus omega naught squared divided by 2 delta theta. This is for the second phase of motion, so it's going to come to rest, so the final angular speed is 0. The initial is what you found in the previous step. We're not using the 20 times anymore, now we're using the 6 times. So that's 6 revolutions, also converted into radians by using our conversion factor 2 pi radians per revolution. When you put it all together, we should be getting negative 8.36 radians per second squared. Notice the problem only asked for the angular acceleration, didn't say magnitude or direction, didn't specify. We should be getting a negative though. If you're not getting a negative, you're doing something wrong, because of course it has to come to rest. We should have a negative angular acceleration as it slows down or loses speed, angular speed, at a rate of 8.36 radians per second per second. As you're going through this, you want to be thinking what units should be going for, because of course we want to put in standard units. Now our standard units are radians per second squared. That's why we had to do our conversion factor using 2 pi radians per revolution to get out of revolutions. However, the problem never actually specifies what units to use for your angular acceleration. You want to think, what are some other valid units? So I want you to pause the video here and think about it. And you may have already done it this way, which is why you may not even have the solution that I showed here. So pause the video and think it through. So other valid units would be revolutions per second squared. So if you went from the original part of the problem and just did omega naught as delta theta over t and never converted into radians, you'd have 20 revolutions for 5 seconds. So that's initial angular speed of 4 revolutions per second. Those are valid units. Putting that into our time-independent kinematics equation, I'm never converting. You have revolutions per second squared and that on top, and the bottom is revolutions. The units still work out to revolutions per second squared, which are valid units. And so if you had this as your solution, this would be absolutely fine, having an answer of negative 1.33 revolutions per second squared. If the problem doesn't specify, either sets of units are absolutely fine. Now here's some things to consider. That if you went in a slightly different order, or you converted everything ahead of time and got some answers, or used different set of equations, you might get answers that are slightly different from mine. We've seen this so many times throughout the year. So if you didn't get exactly 8.36 or 1.33, you got something slightly different, that's absolutely fine, nothing wrong with that. The other thing to consider is, I know some of you who have already seen the radian in your math classes, you're used to answering in terms of pi. For example, an answer of 2 pi, an answer of 5/2 pi, or something like that. You're not allowed to do that here because, of course, while we're using pi as part of our conversion factor, we do have to consider this is a science problem and everything has significant figures. So you're not allowed to answer anything in terms of pi, since pi is a number and we want to always get our answer with a proper number of sig figs. Since everything in this problem had 3 sig figs, we just want to get an answer that has an answer with 3 sig figs in it. Let's move on to problem 4. So go ahead and again, read it, solve it, come back when you need some hints. Again, we have a problem that is broken into separate stages. So you really want to try to visualize what's happening in each stage. We have our initial motion, and then we have a change in motion, an angular acceleration. Letter A only asks about our tangential speed at the end of the acceleration. So we want to make sure we're using the right value here. That's going to be the 3.2 revolutions per second. But here it is asking for a tangential speed. So we want to make sure we're doing our conversion here, where V tangential speed is equal to R omega. Put the numbers in, and we should be getting 4.22 meters per second. since we have to answer in meters per second, you have to do the conversion. You can't leave things in revolutions per second here, so you're forced to use our conversion factor of 2 pi radians per revolution. And you notice that the units will cancel. The units of revolutions will cancel, leaving, in essence, radians times meters on top. And remember, the radian itself is sort of a dummy unit. It's just a counter. It's how much of the angle is traversed, and so it doesn't appear in the answer. So, forgetting about the fact that it's radians, we still have meters on top and seconds on the bottom, giving an answer in meters per second. Now in part B, we're doing the angular acceleration part, so we're going from beginning to end. Make sure we're doing, of course, final minus initial. She's speeding up, so we should have the 3.2 revolutions per second as the final, the 0.750 revolutions per second as the initial. Convert both of them to radians by using 2 pi radians per revolution, whether you did it all in one shot, like I'm doing here, you convert it first, whatever. You should be getting about 12.8 radians per second squared. The problem, again, did not actually specify which using radians per second squared or revolutions per second squared, and so if you went through without doing the conversion, you see the answer is also given in revolutions per second squared, and those are equally valid units.